Okay. So again, this is the first of the fall clsp seminar speakers. Katrin Erk joins us from University of Texas at Austin. She originally started at Sarlin, got her PhD, spent some time there doing some research in frame semantics, and now is doing a lot of really great work in distributional models for semantics, where she works with some other folks that we're aware of, Jason Baldridge and Greg Mooney, one of which is mentioned here on the slides. So a number of us here know about Katrin's work, at the least because of the seminar we ran last semester, the Tycho reading group, which did a whole series on distributional models. Katrin was invited because of all these different authors that have been pushing this, which has become a sort of hot topic within the ACL community. We're especially excited by what Katrin's been doing. So, take it away.
Thanks for having me. Talk topic today is how geometric should our semantic models be. So let me first just briefly introduce the kind of models that I'm talking about. Vector space models that can be used for describing or characterizing words. The underlying idea is that we can represent a word through the context in which it has been observed. So using a really tiny sample corpus of 2 occurrences of the word bathtub, he found 5 fish swimming in an old bathtub, and he slipped down in the bathtub. So the context in which the word bathtub occurs here are these 2 sentences, and we can represent them by just counting the words that we find, which gives us this table of counts here. And we can interpret this table of counts as a vector, where each of these words that we've seen in the context of bathtub, a, down, find, fish, etc., is a dimension, and the co-occurrence counts are the coordinates of the word bathtub in this space. What this gives us is that we can then represent words as points in a high-dimensional space where the dimensions stand for context words or other sorts of context items. Bathtub probably would be down here in this toy representation that's 2-dimensional. Water might be here. The word money may be down there.
Before you go further, can I just ask, what are the coordinates of your space?
The coordinates of the space can be different things. They can be words that you observe in the context of, say, bathtub. So the way that I've done this here, the coordinates are words, so things like a, down, find, and fish. But they don't need to be words. They can be, for example, if you present your sentences as syntactic trees, you can cut up the syntactic trees and have the dimensions stand for snippets of syntactic tree. Or you can do the representations in terms of logical form and have the dimensions represent something about other predicates around bathtub and how they connect to it. And what this buys you, representing words as points in a high-dimensional space, is that you can then talk about similarity of words in terms of proximity in space. So we can model how semantically similar 2 words are by how close together they end up being in space. Because if 2 words are semantically similar, they will tend to occur in the same contexts. If they tend to occur in the same contexts, they should have similar tables of counts, and similar tables of counts translate into similar vectors. And one way in which we can compute this is as the cosine, so which basically measures the angle between the vectors. So as I sketched this here, bathtub and water would be relatively similar because they tend to occur in similar contexts, even though the vector for bathtub is overall much shorter because in a large corpus, bathtub is probably going to occur less often than the word water, whereas the word money, which also occurs a lot, like water, will be more different from bathtub just because the structure of the counts is different. It tends to occur with different types of words. So, again, representing words as points in high-dimensional space, and the main point of it is we can predict similarity of words as proximity in space. And this has been used in a lot of different ways. This being able to predict semantic similarity through co-occurrence counts. In computational linguistics, it has been used in information retrieval, where pages that are similar to the query might be retrieved. To induce word senses, you group together occurrences that are similar in space. To learn or extend ontologies, you can put a new word into your ontology in a place that is where other similar words are located. But vector space models have been used not just in computational linguistics, but also in psychology, where proximity in space has been used to predict all sorts of phenomena linked to human concept representation, like predict explicit similarity judgments that people make. So people have been asked, how similar are king and queen, how similar are king and cabbage, and then you can use a vector space model to predict these human judgments. Vector space models have been used to model priming, which is this phenomenon that if you've just seen a word like cat, you're faster now to react to the word tiger, because semantically similar words, so a word primes you to react to semantically similar words faster. And you can use vector spaces to actually predict when priming is going to occur. Vector space models have also been used to detect synonyms and predict defining features of concepts, and loads of other uses besides. A brief word on terminology here. So I'm talking about vector space models. What I mean is distributional models that occur in a vector space. What I mean by that is, so distributional models are models that use context of occurrence the way that I've described it to you now. Vector space models technically are models that use some sort of space to locate words or characterize words. You can have models that are distributional, but that do not rely on linear algebra, like topic models. Well, you can squeeze them into a vector space, but originally they don't need the linear algebra to function. The other way around, you can have models that describe words in a way that is a vector space, but that is not distributional. In particular, Jardenforce's conceptual spaces use a space where you'd have a dimension like the brightness of a color or the degree to which a taste is sweet. So you can, again, describe entities in terms of this space, but that's not distributional. So here I'm going to be mainly concerned with models that are both distributional and vector space. And I'm just going to say vector space models for short. So, in a nutshell, what I'd like to talk about today is how can we use these vector space models to describe word meaning and sentence meaning. And for word meaning, what I'm going to argue is that word senses are a really tough thing to model. Word sense disambiguation is still a very tough thing to do for machines, and is also tough for annotators to do by hand. So vector space models are good in that they allow us to describe word meaning without having to rely on dictionary senses. And then a kind of logical next step is to say, okay, if vector space models are so great for describing, characterizing the meaning of individual words, can we also use them to describe the meaning of larger phrases or whole sentences? And I'm going to look at a couple of recent approaches that do this, and also talk about an alternative that we've been working on that combines vector space models with a different way of describing sentence meaning, namely through logical form. So, first I'd like to try and convince you that word meaning is really a tough phenomenon to model. Here's an example by Diana McCarthy. the word match, the noun match, has 9 senses in WordNet, and as usual for WordNet, these senses are very fine-grained, so some are not really easy to distinguish. Among these senses, we have sense 1 and sense 3, which both refer to this burning little stick of wood. And then, quite different from these senses, we have sense 6, a person regarded as a good matrimonial prospect. Sense 8, a pair of people who live together. And sense 9, something that resembles or harmonizes with something else. So sometimes it's relatively easy to see how to do the word synthesis migration task, which is to take this list of senses that WordNet gives you and pick a sense that applies to a particular occurrence. So in this first example here, I struck this match and poured the gasoline. It's very clear that this is the lighter sense of the word. Stick this label to the occurrence and be happy. But how about the second sentence below? This is at least 26 weeks by the week in which the approved match with the child is made. So the context of this sentence, it might have something to do with adoption, I guess. So if you think about the senses that we had on the previous page, the lighted piece of wood senses are clearly out. Well, that's easy. But apart from that, it's closer to the second group of senses, but none of them really fit well. So maybe sense 9, something that resembles or harmonizes with, because it's kind of the child harmonizes with the family that it comes into. But if you look further at the gloss of this WordNet sense, it's about the tie makes a good match with your jacket. Is that the same sense? Not quite. It's something related to it, but it doesn't feel right to assign this sense. Or sense 8, a pair of people who live together. Yeah, in a way, but again, it's not exactly that. So a typical way of handling word meaning is you get this list of dictionary senses, say from WordNet or Ontonotes, or pick your favorite dictionary, and for each occurrence of the word, you pick one sense out of that list. But this is a task that is difficult for machines. If you look at accuracy of word synthesis migration, which is still for WordNet in the range of around 75%, similar with other dictionaries. And it's also a task that is difficult for human annotators. So if you look at inter-annotator agreement, using WordNet senses, and you get an inter-annotator agreement of 67% to 78%. That's really not great. This is surprising, because if this is how people deal with word meaning, if it is by mentally picking one sense out of their dictionary list, then they should agree more often, shouldn't they? So if you use more coarse-grained senses than what WordNet offers, then you can do better. So you get an improvement in word synthesis migration accuracy, also inter-annotator agreement of about 10 points, but it still doesn't solve the problem completely. And that is actually not so surprising when you look at examples like the match example on the previous page. Yeah?
So once you evaluate the task with human annotators, how much context do they have? Like, are they present with a single sentence or like a paragraph?
It depends on how the annotation task is set up, but usually they would have 1 to 3 sentences of context on either side. But it's really very tough. So when I was in Saarbrücken working on frame semantic analysis, we did annotation with FrameNet senses, which are more coarse-grained than WordNet for German. And it was really surprising to see we did word meaning and semantic role annotation, and about 3/4 of all the annotator questions were about the word meaning. And sometimes they debate a single sentence for an hour and still not agree. And that was with looking at as much context as they liked. So there's just something about this task of pick a single best sense that's really tough. So one possible answer to why it is so difficult to do this pick a single best sense might come from psychology. So if we accept that, like some psychologists say, word meanings link to mental concepts, or as Murphy says, word meaning is made up of bits and pieces of conceptual structure, then what psychologists have found out about mental concepts might also apply to word senses. And in particular, mental concepts, so the by far overwhelming theory in psychology now is that mental concepts have fuzzy boundaries. So there will be some category members which are clear members, and there are members which are, yeah, well, they could go into this into this category, or they might not. And there are also typicality effects. So some category members are perceived as being much more typical than others. And so if we get the same effects with word meaning, then it wouldn't be surprising that we'd have these cases where annotators debate for an hour and still not agree. That might just be the stuff that falls into this fuzzy boundary, where some annotators say it's still in, others say it's out. And to explore this, we did an annotation experiment that we set up in a different way from how word census immigration is usually done. What we did was we gave annotators the full list of WordNet senses. So like for the word paper, we have the senses material from cellulose. I'm abbreviating the senses here. They got more description than what is here. A report, a publication, a medium for writing, etc. And we asked them, for each of these senses, please give us a rating on a scale from 1 to 5, saying to what extent the sense applies here. And here's an example for one sentence. This can be justified thermodynamically in this case, and this will be done in a separate paper which is being prepared. We had 3 annotators in this part of the experiment, and here's the ratings that they gave. The first annotator said that, so here's how to read this. Annotator 1 said sense 1, the material from cellulose applies to a degree of 4 out of 5. Sense 2 applies to a degree of 3 out of 5, and so on. And so you can see some patterns emerge. Sense 5, which is a scientific paper, got a rating of 5, absolutely, from everybody. Then there's sense 2, which gets a medium to high rating from everybody. Sense 2 is a report. And annotator 1, but not annotators 2 and 3, also saw senses 1 and 7 as being applying, so material from cellulose and a physical object. So annotator 1 diverged here from the other annotators, but did so in a very consistent manner. So it looks like this annotator really perceives the physical piece of paper sense when they talk about the scientific paper. So what we see here is that, and what we saw overall in this annotation task is that annotators did give us graded ratings. They used the whole scale from 1 to 5. There seem to be idiosyncratic differences in how people perceive the meaning of a word in a particular occurrence, and that is okay. That's not just an error. That is not just annotator disagreement. That is idiosyncratic differences in how people perceive meaning, and we may want to take that into account. So a caveat on this was a relatively small annotation study. So in the first round we did 11 lemmas, in the second round we did 26 more lemmas, and in the first round we had 3 annotators, in the second round 8 annotators. So annotators gave us a rating on a scale from 1 to 5. So what we found was that the annotators agreed quite well. Although here, if you have these graded ratings, you don't count just percentage of absolute agreement. You can't do that. You do a correlation, and we had a highly significant correlation between any pair of annotators here. And we also had a highly significant correlation with traditional word sense annotation of the same data. And yeah, as I said, the annotators made use of the complete scale. They didn't just choose 1 or 5, but used everything in between. Very often they gave several senses a high rating. Like in the paper example that you just saw, the scientific paper rating got the scientific paper sense got a high rating, and the report sense also got a high rating. And we often had that annotators chose more than a single sense. So that might also be part of the problem. If several senses apply, how does an annotator choose? And in our example, they could just give a high rating to multiple ones. And interestingly, it was not always the same senses that got a high rating together. So you could imagine that it's always the report and the scientific paper that get a high rating together, a low rating together. But it's not that. Annotators kind of mix and match senses individually for every individual sentence. Here's an example where they did that. The target word here is dismiss. And so the sentence was simply thank your gremlin for his or her opinion, dismiss him or her, and ask your true inner voice to turn up its volume. And the word dismiss has senses that are bar from consideration, like dismiss an idea, and also persuade a person to leave, so dismiss somebody. And here, as you can see, it's kind of both, because this is a metaphorical gremlin that you are persuading to leave, and by doing that, you're literally barring some idea from consideration. We also did a second annotation experiment. So in this first annotation experiment, we did use WordNet senses, and our annotators gave graded ratings for the WordNet senses. In the second experiment, we did away completely with the WordNet senses and just gave people 2 sentences at a time that have one word in common. And we asked them, to what extent are these 2 usages similar? So we have here convicted of criminal charges, and up here explicit or implicit charges that practical thinking is merely a knack or form of cleverness. So down here, this is criminal charges, and up here, this is charges in a debate. And 3 annotators again. 1 annotator gave a rating of 2, so these 2 uses are somewhat similar, but still mostly different. 3 is kind of, so 2 was mostly different, 3 is similar, and 4 is highly similar. So you can see, on average, the annotators thought these 2 uses to be kind of medium similar. So again, caveat that this was a relatively small data set, but again, inter-annotator agreement, we found highly significant correlation between pairs of annotators and highly significant correlation of these pairwise ratings with annotation in terms of word senses. So that's encouraging. We can describe word meaning in different ways and get ratings that are actually correlated across different styles of tasks. And again, the annotators used the complete scale. So this study here gave us a way of describing word meaning without referring to dictionary senses at all, just through similarity of individual word usages. And that, in fact, is also what we can do using vector space models. So,
Before you go on, can I ask you a
yeah,
question?
go on.
The claims that you made said highly significant correlation.
Yes.
You're not claiming that the correlation is high, right? You're simply claiming that the existence of correlation is supported. I'm trying to interpret that statement precisely, saying highly significant correlation between pairs of annotators.
Yeah, so the correlation...
Primary test where the null hypothesis says they are not correlated at all and the argument says they are, and you're finding that there is correlation? Or is it something else?
So what we did was rank-based correlation using Spearman's row. So what we get out of that is both a degree of correlation and the degree of significance. And significance was off the scale in all pairwise comparisons. And the row values were, what was that? Was on the order of 0.5, 0.6, which means that, which in absolutes measures is of course not so high, because it means that about a quarter of the variance in the data is explained by the correlation. You have the usual R squared.
No, that's what I was looking for, because I wanted to get a sense of what you mean by correlation. That the fact that there is correlation is not under dispute.
Yes.
And one can argue how much the correlation is and argue about the particular type of correlation.
Yes.
And so on. And the Spearman rank, the correlation is of 0.516.
Yeah.
Is that true about the previous couple of things also?
Yes, we use Spearman's rule throughout. Only rank-based correlation because the data is not normally distributed.
And the rank being of these 5 or 7 senses, which one do you give the highest rating, which one is second?
Let's see, so
If I have 2 annotators and 1 word.
so let's see, how did we do that? I think it was across all the annotated sentences. So one lemma across all the annotated sentences, ranking by annotator 1 versus annotator 2 in terms of the ratings that they gave. All right, so we can describe word meaning without referring to dictionary senses by talking about similarity of different usages of the same word. And we can do that using vector spaces as well. So the aim here is to say we want to describe, we want to have vector space representations point in space for individual occurrences of a word, so that the criminal charges might be here, and the charges that whatever is only a knack might be here. And then what you can do is you can describe the whole set of meanings of a word just through the similarities between the individual occurrences. Some might just cluster, like for a word like bank, you would expect to have one big group of occurrences down here for the financial bank and one big group of occurrences over here for the Riverside Bank. But for other words, like, I don't know, leave or show, you might expect to see more of a smear all through semantic space, because you don't have clearly distinct senses. And you could model that just because each individual occurrence would be a point in space. So yeah, the aim is to have one vector space representation, one point in space per occurrence of a word, where occurrences might be arbitrarily close or distant. One problem with that, if you compute your vector space model of a corpus, what you get is one point in space per word, which would conflate the financial and the Riverside sense of bank, rather than 1 point per occurrence. So what we need to do is we need to compute somehow a representation for each occurrence if we only have a representation for the word as a whole. And this task has been called contextualization. So what we want to do with this is as follows. If we have this points in space for individual occurrences, well, what do we do with that? How do we read off what the word means once we know it's there in space? And the only way that we can do that with a vector space model is through comparison with some other vectors, through similarity. And the way that we do it is by predicting the appropriateness of a paraphrase. So if you have a sentence like, he caught the flu, is this occurrence of catch like grab, or is it like contract? Doing this paraphrasing task is good because we can use paraphrases instead of word senses, and we can describe word meaning through paraphrases without having to say, well, these group together and form a sense, and these group together and form a sense. And paraphrases have a lot of applications. So how do we predict the paraphrase appropriateness? In a case like here, we would compute a point for catch in the context of flu, which might be here, and then you compare it for similarity with the vector for grab and the vector for contract, and you predict a degree of appropriateness of the paraphrase which is proportionate to the similarity of your in-context vector for catch to either grab or contract. And there are actually data sets where you have paraphrase appropriateness for words in context. And the most used data set is the McCarthy and Navigli one. So, how can we do this, computing these individual points for occurrences rather than complete words? There are a couple of groups of approaches. Either you have this vector for bank, mix financial, and Riverside, and given a context, you kind of bend the vector, you adapt it to the context. Another way of proceeding is, instead of computing this one vector for bank, you take the individual occurrences and you cluster them beforehand. And then when you have your occurrence, you choose among the clusters, or you compute a weight distribution of the clusters. A third group of approaches is to use language model, basically. How likely is each paraphrase to occur in this place? I'm not going to say a lot about this group of approaches because they are not vector space based. So the very simplest approaches of doing contextualization is, the very simplest is, I guess, vector addition. So you have the vector for catch, you take the vector for flu, and you add them both up to get the vector for catch in the context of flu. A variant of that is, instead of doing vector addition, to do component-wise multiplication. You basically take the vector for catch and you weigh its dimensions by the vector for flu in order to get a re-weighted vector for catch in that context. There are also approaches that use topic models and similarly non-negative matrix factorization. So you do a topic distribution over all contexts, and then you compute the probability of each topic given your target word and given the current sentence context. You can also use vectors of syntactic neighbors. So topic models and likewise the vector addition uses the whole sentence as a bag of words, and whereas some other approaches only look at the syntactic structure. So you have catch, flu, and if you had a larger sentence with a lot of other things, those would not be used, but only the direct syntactic neighbors of the word that you're trying to disambiguate. What do I have here? And here what we once did was, instead of doing one vector for bank, you keep all the individual occurrences around, and you only when you see a current occurrence do you compute a vector for bank from those other occurrences that are most similar to your current one. There's one approach that I'll describe in a bit more detail here, which uses syntactic context only. So if we look at the example of he caught the ball, what we did there was to say we want to compute the meaning of ball in the context of catch. So it's not the social event, it's the sphere sense of ball. And at the same time we want to compute the meaning of catch in the context of ball. So it's not contract as in catch the flu, it's more like grab. And we want to compute them as follows. We want to compute the meaning of ball in the context of catch. It's not the social event, because instead it's closer to things that are typically caught. So social events are not typically caught, but spheres are. Conversely, contracting an illness are not typical actions that are performed with a ball, but grabbing is more likely. So we use selection of preferences for disambiguation, and in particular we use the selection of preferences of catch to disambiguate ball, and the other way around, the inverse selection of preferences of ball towards the predicates that occur with it to disambiguate catch. So that gives us representations for words that are not an individual vector, but a collection of vectors, one for the word itself. And here for catch, we would have one vector describing typical subjects of catch, one vector describing typical objects of catch. We might even describe a vector describing predicates that typically take catch as a complement. And the other way around for the word ball, we could have one vector describing typical modifiers of ball, one vector for predicates that take ball as a subject, one vector for predicates that take ball as an object, so throw a ball, catch a ball, organize a ball. And as you can see, in these vectors, we still have the mixture of senses. So throw and catch you do with a sphere, organize you do with a social event. So, and these selection preference vectors are actually pretty simple to compute. You go to a corpus and you collect, say, modifiers of the word ball, and you just add up their vectors, and that gives you a selection preference vector. And then you do this mutual disambiguation. As I just said, we want to disambiguate the word catch using the predicates that typically take ball as an object. So we combine the vector for catch with the vector for that has throw, catch, organize in it. And we disambiguate the word ball using typical objects of catch. So this is kind of one of these vector bending approaches. We bend the vector for ball into the direction of typical objects of catch. We bend the vector for catch in the direction of typical predicates that go with ball. So this is because so we have a vector for catch that mixes multiple senses, that mixes the grab sense with the contract illness sense. And what we want to do is we want to modify this vector such that it fits the current sentence context. And so I was saying bending the vector for modifying it to fit the current sentence context. And you can modify it in the simplest ways by adding it up with another vector, or by doing this component-wise multiplication, which is basically a reweighting of all the dimensions. Does that make it a bit clearer? Yeah, so this is one of the syntactic neighbors only approaches. And as you can see, there's a lot that this approach disregards. If it only looks at the direct syntactic neighbors of the word catch for disambiguation, it disregards the whole rest of the sentence. Evaluating contextualization approaches is unfortunately a big mess. And it's really hard to compare different approaches because people use all sorts of different evaluation measures. So in the McCarthy and Navigli datasets, this is a dataset where people picked paraphrases. So they were given a sentence like, he was arrested on charges of whatever, drug trafficking, and then the human annotator would write offense or accusation or however many paraphrases they wanted. And so the paraphrases there are weighted by how many annotators picked it. And a lot of people use these weights in evaluation by using generalized average precision, where they credit the model-generated ranking based on the gold weights, where the gold weights are how many people picked this paraphrase. Another way is to do basically the rank-based correlation again, using Kendall's tau this time, over all sentences. So how well did the model predict how well the paraphrase catch would fit in sentence 5 versus how well the paraphrase offense would fit in sentence 27, which is an extremely hard evaluation, but also one where I'm not sure that that really helps for applications doing this basically mainly rewarding cross-sentence uniformity. And what we did, and what I would propose doing, is basically just to do precision and recall, ignoring the paraphrase weight, ignoring how many people picked a particular paraphrase, because that is relatively noisy anyway. So evaluation, as far as possible, you can see it's a mess because of the evaluation measures picked, but also because people built their vectors on different corpora of vastly different sizes. So BNC is about 100 million words, GigaWord is about 1 billion, UK WAC is about 2 billion, and of course that's going to have a big effect on how good your model works, and so we can't really compare. But anyway, if you want to do this, then evaluation on part of this paraphrasing data set, the Tatra et al. Syntactic method got the best gap, and if you use the whole paraphrasing data set and UK web as corpus, then the Van der Kroes topic modeling like approach got the best results. But here's our precision and recall measure, which I think says more about where we are at the moment. I unfortunately only have that for our current our recent model. So this is at different levels in the model's predicted ranking, what's the precision and recall. So if we look only at the highest ranked paraphrase that the model proposed, then we get a precision of almost 50% and a recall of about 14%. That is, very often more than one paraphrase applies, and we are only getting a small part of those. And we're getting about half of the paraphrases right that we're predicting. If we look at the first 5 paraphrases that the model predicts, we get a recall of about 50%. So if we look at the first 5 paraphrases, we catch about half of the good paraphrases that humans propose at a precision of about 36%, which is not amazing, and is surprisingly similar to the kinds of results that people get in unsupervised word census immigration. Yeah?
So you measure recall by how many of the possible paraphrases you identify, even though you allow your system to only pick one?
Yeah, so I allow my system to rank them all. And here I'm looking at, if I look only at the very first of the ranking, what's the recall? And here's, if I look at the first 5 in the ranking, what's the recall?
But the recall is how many of the totally proposed
by the humans, yeah.
So then what's the ceiling of this? Recall at 1?
Recall at 1 is if in this prefix of the model ranking, all of the human proposed paraphrases are in. That's when I get a recall of 1.
Yeah, he's asking what's the best you could do at recall of 1, given the number of different...
So supposedly if you have 5 humans proposed annotation, the best you can do is 0.2 recall because you're only picking 1?
Well, at the first ranking, yes.
So what's the maximum we can do there in that particular level?
I haven't checked that, actually.
There is a measure, I think you probably know it also, that it's called precision at R. So what you do is you set R for every lexical item to be the number of whatever sensors or clusters that the human will pick. And you always measure precision of that. And then it's a single number whose highest value is going to be 100%. So if you get all the 3 sensors that the human picked into your top 3, then you're at 100%. Otherwise you lose. And then you can reduce it to a number that normalizes across your lexical types. But otherwise, the other question that compounds this thing is that different words have different number of reference sensors. And so what you give us is
paraphrases.
a gross number over all of them. Like this example of 5 sensors and 20% is the maximum reachable at 1. For a word that has 5 sensors, you're mixing their words that have 2 sensors or 7 sensors or whatever it is, and then it's hard to make sense of it.
Yeah, it seems a bit unfair because you're telling your system predict all of the 5 sensors, but it'll only give me 1 answer.
One answer.
Well, I mean, these are only snapshots. So the best way of viewing this is actually by having the graph of showing the precision and recall over the whole ranking.
Still, what Sanjit brings up is you can never have recall of one because, well,
you can if you're.
You cannot have both precision of one and recall of one.
Well, you can if you rank all the human proposed paraphrases higher than the non-human proposed paraphrases. Then at the point where your list is long enough for all the human proposed paraphrases, then you'll be at 1. That's right. Yeah. So you'd have to look at that by.
That's why the precision in R does exactly that.
Okay.
Where it sets that number to be the number of human preferred senses.
Except that we don't have senses here.
Or whatever.
Yeah, paraphrases. Okay. Yeah, it probably makes sense to do that. All right. So what I would say we should have is the ability of modeling individual occurrences and the similarity without having to go to dictionary senses. And vector space contextualization models can do that. But we do need better models because what we currently have does about as well as unsupervised word sense disambiguation, roughly. Okay, so going on to vector space models for sentence meaning. So word vectors can predict word similarity. Can we, in the same way, predict sentence similarity? There are data sets with human similarity ratings for 2-word phrases, and people have used those to see, well, how well can we do in predicting phrase similarity. Possible applications, one possible application is very clear, paraphrase prediction for larger sentences, and then any other task that can be phrased in terms of sentence similarity. So, but what are sentence vectors in the first place? So word vectors you can compute by just looking all the contexts in which a word has occurred. You can also do that for short phrases, but as phrases get longer, you cannot do that anymore because they just don't occur often enough that you could get a distributional profile for them. Instead, what people do is to compose the word vectors, so put them together in some way to get sentence vectors. And the simplest methods are actually, and funnily, the same ones as you've seen above, vector addition and component-wise multiplication. And actually, they are better described as methods for getting a phrase vector than methods for getting a word vector in context. Then there's this sequence of papers by Clark and Grafenstede and Saderzadeh and colleagues. What they've done is to give words representations that are tensors, where the type of tensor depends on categorical grammar style type for a word, and then you compose the tensors for the words according to their type. And what they propose for transitive verbs is as follows. We have for the verbs tensors that describe co-occurrences of subjects and objects. And in order to describe the meaning of a verb in a particular, or the phrase that consists of a verb and a subject and an object, you do a tensor product of the subject and object, so you combine subject and object, and then do component-wise multiplication to filter the general meaning of the verb through this particular subject and object in a way. So you have one tensor that describes the whole subject-verb-object combination. Other approaches to say, well, let's do adjectives as matrices and nouns as vectors and apply the adjective matrix to a noun vector to get a vector for the adjective-noun pair. And again, this is only for adjective-noun pairs, so all that I've shown you so far are approaches for relatively short phrases, 2 words, 3 words. And the only one that I'm aware of that can do phrases of arbitrary length, apart from stuff like vector addition, is Socher et al., who do a tree of vectors. So you have a syntactic tree, and for the individual words, and for the phrases at each level in the syntactic tree, you get a vector. So you get a tree of vectors, one at the root for the whole sentence, but also the individual ones below, using recurrent neural networks to compute them. And then they can do sentence similarity based not just at the similarity of the root nodes, but on pairwise similarity of any two nodes. So you have a much more fine-grained representation of a sentence than if you just have this one tensor for the whole thing. There's a lot of problems actually with these phrase vectors, I think. One is human language sentences can be as long as they like. And if you have a vector or tensor of fixed dimensionality, how much can you fit in? And how much information loss do you have as your sentences grow longer and longer? Which is not a problem for the tree of vectors approach, because that grows as needed. So a related problem is if you want to compute sentence similarity, you need to integrate the whole sentence somehow, so you can get one notion of similarity between the two. But on the other hand, if you want a fine-grained representation of what the sentence means with all its intricacies, then you want to keep the components apart. So what do? Integrate or keep apart? And on a technical level, a lot of these approaches can't compute similarity for sentences that don't share the same syntactic structure, because they'll just be tensors of different type, and you can't do anything with those. And also, how do you represent function words? So what's the vector for not? What's the vector for the? Just the distributional contexts? That's going to be awfully noisy. So what we did instead was to say, let's describe a sentence through logic plus vector spaces, because so vector spaces have this nice and graded notion of similarity, and can represent all the flexibility that you need for degrees of similarity of word meaning, whereas logical form can do all the nice stuff like handle negation. It can handle all the function words. It has modals, etc., and can handle the exact representation of complex sentence structure. And the way that we do this is we use Boxer to compute logical form for a sentence. And then each predicate symbol is associated with a contextualized vector for its word. So if you have the programmer fix the bug, then what Boxer will give you is logical form, which is neo-Davidsonian, with the little e's in there. So you have a fixing event where the patient is a bug. And then you have, for the predicate fix, you have the general vector for fix, and you have the contextualized vector for fix, which we compute off of the logical form here. And once we have this contextualized vector for fix, then we can use vector space to do inferences. That's how you can describe what vector spaces are good at. If this contextualized vector for fix is similar to, or is close to the vector for correct, with some cosine, then we can project a rule that says all fixing events are correcting events with some weight that depends on the cosine or the similarity between fix and correct. Yeah?
Can you just describe the contextualized vector for fix again? Like how is that created?
So you can use all the methods for contextualization that we've described above.
I was thinking you just logical form a big corpus and just create a distribution representation of fix every time it was used in a similar...
We haven't done that yet. I'm not sure whether it'll be useful to have a space that is dependent on logical form. But
you're saying this is preprocessing stuff. Yeah. You're computing the similarity.
Yeah.
Using word and co-occurrence within a sentence or something
Yeah.
Instead of understand.
Yeah, but the contextualization itself, you can do that using the logical form. For example, by saying that fix, the variable here also occurs in patient EX, so you have fix is relatively close in the logical form to this bug thing here, so you can talk about other predicates in the logical form that can help you contextualize fix and compute this here. So for computing the vector space, the dimensions itself, I haven't used the logical form just because it takes so long to compute logical forms for everything, and there I don't really see the advantage of having a logical form-based space. But for the contextualization, I do see the advantage, because there you do get different notions of similarity from what you get in the syntax. Yeah.
So the role of the logical form is restricted at this point to the contextualization process?
No, the logical form is where we describe the meaning of the whole sentence, and that's also where we do inferences. So if we wanted to do, for example, does this entail that the programmer corrected the bug? Then we try to do the inference in the logical form using these inference rules that we have projected from the vector space.
So talk about the paper up. We should interpret this as Markov logic? Right? So
We use the Markov logic to deal with these weighted clauses. Yeah.
In particular, I misunderstood this until I pulled up the paper. This is not saying that with such and such a probability that this implication is true for all E. Rather, it's saying that for all E, you have a potential function. For each E, you have a potential function in your Markov logic network.
Mm-hmm. Yeah.
So it could be true for some E and not for other E's. The idea is that for all E, for every E, you have a preference. For every E such that fix of E is true, you have a preference for corrected E also.
Yeah, although this formulation here we can get away with because we're currently using text snippets that are small enough that we only have one fixing event in there. So if we had larger text, we would want to say, well, fixing event number 689, that has a particular weight for being also a correcting event.
Good. So in case my question wasn't clear to everybody, the question is whether the probability scopes over the quantifier or comes under the quantifier, the probabilistic decision. And it's under the quantifier. It's not a probability that it's always true.
No. So we use Markov logic networks to compute with these clause sets that have weighted clauses in there, which do the following. If you have a clause set, you compute all the groundings of all clauses and form an undirected graphical model using the sets of all the groundings, and you compute the probability of truth assignments. Basically, the probability of a truth assignment for your variables increases exponentially with the number of satisfied groundings of a truth assignment. So this is work in progress, though. We have been able to successfully integrate paraphrasing and implicatives. So if you prevent the wine from leaving a stain, then you have the question, does the wine result in a stain, or does leave here mean flee? But also, does prevent mean that it did or did not happen? And we can model the interaction of that. But in general, using MLNs is sometimes painful because it's incredibly memory intensive. So you compute all the groundings of a set of clauses, it just explodes in memory. So what we do is we use transformations on the logical form that are not safe in general, but are justified for the natural language semantics that we see. So what I've been talking about in conclusion is dictionary sense approaches to polysemy are often difficult. And we did an annotation study using these graded ratings. where we found that human annotators used the whole range of ratings. They mixed and matched senses, and we saw individual differences in the perceived meanings. I've been proposing to use vector space models to represent word meaning without the dictionary senses. So contextualization means computing individual points in space for each occurrence. Moving from word meaning models to sentence meaning models, we hope to be able to predict phrase similarity, but there are problems like scalability and fundamental questions like, what do we want our semantic model to be able to do? Does it suffice for it to be able to predict similarity, or what do we expect of our semantics? And we can actually look at a similar debate in the context of symbolic versus connectionist AI to the question of how far can we get with similarity. So what I've been starting to look at is combining logic and vector spaces using Markov logic networks. And there's a lot to be done. So for the contextualization, as you can see, better models are really needed. Maybe using supervision, given that current models are somewhat comparable to unsupervised word synthesis immigration. Sentence representations. Representing larger phrases is still a big problem, and we need to think about what the tasks are for a semantic model, what we want it to do. Logic plus vector spaces, so far I've only looked at paraphrases for individual words. So can we talk about similarity of larger lambda expressions to get at multi-word paraphrases? Another question is, well, we know what the semantics is for logical form. It's usual model theoretic semantics. But what's the semantics of a vector space? All right, that's it.
So I'm still trying to understand the last piece of work a little bit better. One place where my understanding is running into trouble is, aren't you going to get similarity between things of different semantic types? Is there a type theory here? Like what happens if a predicate ends up looking similar to an entity?
So far I've gone around that problem by assuming two tasks. One task is coming up with paraphrase candidates, and another task is rating the degree of applicability of a paraphrase. So if you do that separately, then this making sure that you don't get similarity between different types is something that is a problem of coming up with the paraphrase candidates. So if you start out with good lists of paraphrase candidates, like using human-generated lists of paraphrases or using the full list of possible paraphrases in WordNet or whatever, you don't run into that problem. But in principle, if we were to use an automatically extracted list of paraphrases, like the work of Chris and Ben, we might run into this problem of generating possible type clashes, and then that would be something to take care of at the level of computing the projections. So projecting information from vector space to the logical form.
Yeah, I guess my question is, when you're generating a rule like for all E, F of E implies G of E, what happens if F and G take different numbers of arguments?
Yes, that's what I'm saying. Currently, this cannot happen because we are using lists of potential paraphrases.
Oh, I'm sorry. So you're saying you completely eliminate the problem?
Currently, yes.
I thought you were saying what you did would probably do a pretty good job.
So in our current system, it completely eliminates the problem. But in future, if we use different lists of potential paraphrases, we could have that problem, and then we would have to take care of that. If you have a list of possible paraphrases that are all of the same type. then you can't run into the trouble. Also, I mean, with the Neo-Davidsonian approach, all the events end up one-place predicates. So the problem would only show up later, I guess, if you'd have an impossible patient for something that's not supposed to have a patient. But we'd still have to take care of it.
Well, I mean, once you, the Neo-Davidsonian semantics starts to highlight a problem that I was also worried about, is you would hope that you would get things like A and B together imply C. Once you start distributing the information across multiple predicates.
Yes, and that's where.
I wonder what the distributional preprocessing could actually do to give you, which is not just about pairwise similarity.
What we would have to do there is to talk about, so you know, of course, the DIRT-style paraphrases that talk about similarity between snippets of syntactic structure. So what you can do is you can extract multi-word paraphrases that are pieces of syntactic structure by looking at similarity of the context in which these snippets of syntactic trees occur. So basically what's at the leaves that you cut off. And instead of doing that, you could also learn similarity or paraphrasehood between lambda terms with this, in the same way by looking at the similarity in the fillers for the variables. And once you have that, you could have a similarity between lambda x a of x and b of x and lambda x c of x.
There seems to be a connection maybe to the stuff that Tom Mitchell has been doing in
Can you say more? I don't know what you're referring to.
well, let's take it off then.
Okay.